Video number 3+, Scientific Certainties and the Universe. Hello everyone. The topic that we shall discuss today is completely obvious for all professional scientists. Well-known physicists, such as Einstein and Feynman, said very clearly that even a fully recognized theory can be disproved at any time by a single experiment showing a contradiction with one of its consequences. However, sometimes our scientists feel obliged to behave as if they absolutely believe in today's theories, especially when they have to teach. And this may propagate in the general population a false idea of science. Today we are going to focus on the notions of certainty and evidence in science and especially in physics. The comparison with mathematics is instructive. In mathematics, certainty always relies on evidence, the criterion of truth being the proof, which relates every statement to the starting axiom of the theory. The axioms are not discussed, they are initial working hypotheses whose status and role are now perfectly clear with the development of formal logic. On the other hand, certainties in science are quite rare. They concern objects whose definition must be clear and consensual, and their validity is often subject to conditions which need to be checked carefully. Point 1. Certainties and their limits. It must first be remembered that apart from the certainties deduced from already accepted results, by a mathematical type of argument, most certainties in science are based on experimentation. Experiments must satisfy a certain number of conditions to be credible, but even when they do, they are actually used to verify the absence of contradiction between a conjectured property and quantitative or qualitative observations. An experiment is never proof in the logical sense of the term, because the absence of contradiction with the consequence of the hypothesis does not prove that the hypothesis is true. For instance, the fact that Socrates died does not contradict the hypothesis that he was a human, but he could have been a horse as well. An example of certainty for physicists: the Rutherford experiment. A foil of gold is bound with alpha particles, and it turns out that most of them cross the foil, only 1 out of 10,000 being deflected. Rutherford concludes that matter is mainly composed of vacuum, contradicting the plum pudding model of Thomson. It is even possible to evaluate the diameter of the nucleus. This was the starting point of the modern atomic theory. In fact, there was no certainty here. Some atoms could be hollow, and some others solid. But common sense consists for physicists in assuming that all gold atoms are identical. This is something that we shall never verify. Even if we had the tools to do so, we could only explore a tiny proportion of atoms. Indeed, according to the value of Avogadro's number, in 1 gram of gold, there are more than 3 times 10 to the power 21 atoms. If you just take 1 second to examine each of them, you will need about 7,000 times the supposed age of the universe. At least we can now manipulate the atoms, which is not the case for the astronomical objects at the other end of the magnitude scale. Point 2. Evidence and hidden hypotheses. Implicit assumptions abound in fields such as cosmology, and this opens the door to a considerable mistake, since we will never go to check on the spot. If we seek to establish general rules on galaxies, for example, setting the origin of time as the present, we observe the state of each galaxy at the distance minus d over c, where d is the distance and c is the velocity of light. We therefore have at each distance a limited sampling of galaxies and the same at each moment in the past. Actually, assuming that we have been observing galaxies for a century, it is a little less. That the universe began 10 billion years ago, it is a little more. The proportion of space-time that can have been explored until now represents only 1 over 100 million as a total. So, we cannot seriously apply the law of large numbers, saying that we have representative centers of the whole universe. But this is what astronomers do implicitly. We silence 99.999999% of the universe. I believe there is no other science where one makes such a hazardous, a never-explained gamble. It is therefore not surprising that from time to time astronomers discover strange and unexpected objects, some of them leading to reconsider our knowledge of general physics. It started with quasars and pulsars. We now know almost surely that pulsars are neutron stars. But the nature of quasars is not yet so clear. One can imagine that unexpected objects will appear to observers until the end of times, disqualifying in turn all the theories in force. Are we really certain, in such a situation, to progress towards the truth? And by the way, what is truth in astrophysics? Point 3. When we manipulate ill-defined concepts, all mistakes become possible. Let's talk about the universe, for example. What is that? The naive answer is all that exists. Fine, but what does exist mean here? Exist for us? For humans of the past or for those of the future? How are we supposed to decide between existence and non-existence? With the discovery of radio waves, we introduced an additional sense for our perception of distant worlds and discovered radio sources whose real nature is not always easy to imagine. Just imagine, because there is no question of verifying. Never a human being will observe on the spot. Now, who tells us that we will not, tomorrow morning, or in 10,000 years, discover some means of exploration other than electromagnetic waves? We are certain, or almost certain, of what exists, but never of what does not exist. Unknown objects could modify the laws of our world, especially from large distances. Remember also that in mathematics, the set of all sets does not make sense, according to a theorem proved by George Cantor in 1891. The translation in physics could be that the word universe has no meaning. You will understand that in such a context, any statement concerning the proportion of exotic dark matter, that is to say non-baryonic, in the universe, is about as serious as a conjecture on the sex of angels. Because, to begin with, the universe exists about as much as angels. It is in fact a somewhat megalomaniac concept, aimed at creating the illusion that we intellectually control all of what exists, while our ignorance of the functioning of our environment, even locally, is still almost total. In this context, I am often concerned, especially in cosmology, but not only, by somewhat hasty conclusions communicated prematurely to the general public, while research in astrophysics is made very difficult by the extent of the subject compared to the limited nature of our means of observation. More fundamentally, scientific research can be credible only if it is practiced as rigorously as possible, with a maximum overlap between disciplines, which is not always the case, for various reasons, which sometimes have nothing to do with science.